Hey everybody, welcome back. In this video we're going to look at an application of the photoelectric effect, which is the photomultiplier tube, the PMT. So I'm looking right now at the summary notes, and this shows a schematic of a photomultiplier tube. So we'll talk about how it works, and also we'll develop some equations that characterize its operation. So what we have is a basically very sensitive light detector, and it utilizes the fact that photons can eject electrons through the photoelectric effect. So the basic structure you're going to have is a so-called photocathode. Look, this entire thing, remember, is going to be in an evacuated tube because you're going to have electrons flying around. So this one is what we would call a transmission style photocathode. But the photocathode is going to be right here, this piece of metal inside the tube. A photon comes in, strikes the metal, and there's going to be some sort of transparent window here. And in this photocathode, the photoelectrons are ejected on the other side of the material. Okay, so that's why I call it a transmission photocathode. Some photocathodes, the electrons would be ejected from going in the opposite direction, so they're ejected on the same side as the photocathode. So here is the photoelectron. Now here comes the multiplication part. What you do next is you accelerate this photoelectron using an applied potential difference so that it slams into another metal plate called a dynode. You want this electron, when it slams into the dynode, to deliver enough energy that typically between 2 and 4 electrons are ejected from that dynode. So if this electron hits this dynode, we're going to get 2 to 4 electrons ejected from the dynode. In this drawing, if you can see those faint blue lines, they have 2 coming from this dynode. Then what you do is you accelerate these electrons with another potential difference so that they slam into another dynode. So each of the electrons from the first dynode is going to result in 2 to 4 electrons being ejected from the next dynode. And you continue this process. Typically in a tube you'll have maybe 9, 10 dynodes. In this drawing there are 6. So at the end of the stage of dynodes, you can have hundreds of thousands of electrons leaving that last dynode per incident photoelectron at the beginning of the dynode chain. Those electrons that leave the last dynode, they are collected at the anode plate. And then this is part of a circuit, so all of those electrons that are collected at the anode, they'll be part of a current that you can detect. You can measure the current directly or measure the voltage difference that that current produces. Now that current, that output current from the anode, is still going to be relatively small. So you're going to have some sort of amplification circuit to make it a current that you can actually work with. But that's the general idea. And again, they are very sensitive. You would use a photomultiplier tube in very low light intensity conditions. In fact, if you cool these down to very low temperatures so that you don't get thermal emission of electrons from the dynodes, that contributes to what's called a dark current. So if you cool these photomultiplier tubes down, you can actually detect single photons striking the photocathode. And that's a little bit more sophisticated setup, but you can do that. Okay, and I'm trying to see what else. Oh, I don't know, again, if you can see in this diagram, they have a series of resistors down here. This is how you apply the voltage differences across consecutive dynodes. So when you put this photomultiplier tube in its socket, you supply just one voltage difference. It's typically 1,000, 1,200 volts. That resistor network, it's just a voltage divider network. It'll divide up that applied voltage difference into successive stages. smaller voltage differences to accelerate the electrons across the dinodes. So that's the basic operation, how it works. Now let's characterize the operation with some formulas. And I'm just going to scroll down and you'll see the quantities we're going to introduce right here. So the first thing that we'll write here is the photon rate. So we have a certain number of photons per time hitting the photocathode. So that's my R sub pH. Remember, we talked about the photon rate when we talked about the power carried in a photon beam. So you take the energy of a photon at a given frequency times the photon rate, and that will give you the power delivered at that frequency. So that's the same photon rate. Now, each photon that hits this photocathode is not going to produce a photoelectron. There is a very good chance that a photon will not result in an ejected photoelectron. That photon might reflect, or it just might be absorbed and the energy thermally dissipated. So there is an efficiency called the photocathode efficiency that you see right here. And we're going to use the Greek eta. That's a lowercase eta. That's typical in physics. If you talk about efficiencies, we'll use an eta, different types of efficiencies. So this is just the probability that a photon causes the ejection of a photoelectron. This is just a number between 0 and 1. In fact, you might be surprised that efficiencies are generally not that high. They might be 30% or typically less. And a photocathode material doesn't have a uniform efficiency. It will vary with wavelength of the photon. Okay, so and different materials will have a different range of wavelengths that they'll work at. But you try to get a nice uniform response in the material, but it's hard to get a nice flat response. Okay, so we have the photon rate and the photocathode efficiency. Okay, the next thing we're going to do is we are going to specify the number of dinodes. So that's just going to be capital N, the number of dinodes. And again, that's typically around 9 or so. Now, the next thing, this secondary emission ratio. What is that? Well, that is the average number of electrons that are emitted from a dinode per incident electron. Let me just write that. Maybe I can just type that right here. Let's see if that works. Yeah, that should work. Okay, so this is the average number of electrons emitted, or let's say ejected from a dinode per incident electron. I was going to ask, did I misspell anything? I sure did. There you go. Okay. Now that's around, as I mentioned before, 2 to 4 typically. Okay. But if you know the number of dinodes and the secondary emission ratio, you can then calculate what's called the gain of the PMT. And it's delta to the N. And you can check that. Suppose, let's just pick a low number of dinodes. Let's go with 3, so we can actually trace the electrons through the 3 dinodes. And let's say that the secondary emission ratio is 2, so it's easy to count. So from the first dinode, right, we're going to have a photoelectron hits the first dinode, we're going to have 2, okay, coming from that one. Those 2 are going to hit the second dinode, so each of those will produce 2. So we have 4 leaving the second dinode. Those 4 hit the third dinode, each produce 2. We've got 8 total ejected electrons. And you can see if I take 2 to the third power, I'll get 8. Now remember, typically delta is between 2 to 4, and N is around 9, so these gains can be quite large. Okay, several hundred thousand. Okay, so now, let's define what I'm calling R cathode. That is the rate of photoelectrons, not photons, but electrons leaving the photocathode. So how many electrons per second are leaving the photocathode. I'll call that R cathode. Well, that should be equal to the rate of the photons arriving at the photocathode times this efficiency, this photocathode efficiency, right? Because, again, 8 is the probability that a single photon causes an ejection of a photoelectron. Okay. Well, if we know the rate of electrons leaving the cathode, all we should have to do to figure out the rate leaving the anode is multiply the cathode rate by the gain. So our anode, as I'm calling it, that's the rate of electrons collected at the anode. That's just going to be the gain times our cathode. Okay? Now, we can convert these cathode and anode electron rates into actual currents by simply multiplying by the fundamental charge. Each electron carries the fundamental charge, 1.6 times 10 to the minus 19 coulombs. So if we just multiply the rates, the respective rates, by the fundamental charge E, we're going to have the current leaving the cathode, I cathode, and the current leaving the anode, I anode. Now, it's the current leaving the anode that you're going to detect, amplify, and measure. Okay, but you can also characterize the cathode current in amps. And these currents are going to be extremely small, typically nanoamps leaving the anode. So we're talking about, sub-picoamp leaving the cathode. But there are the equations then that will characterize the operation of the PMT. So you should be familiar with them. I believe one of your homework problems, you're going to design a PMT or characterize it. So you'll use these equations. Okay. I'll also notice that the anode current is simply the gain times the cathode current. So I could write that I anode is just the gain G times I cathode. Okay, so another way to relate the currents. Okay, that's it. Now I looked up here, and now where are you going to see these PMTs used? Again, it's going to be in places where you do not have a lot of light and you need a very sensitive detector. They're also very fast detectors because they use the motion of electrons in vacuum. Okay, and one place that you'll see these is in neutron detectors. So I wanted to show you guys, I said neutron detectors, I'm so sorry. I meant to say neutrino detectors. So neutrinos are interesting particles. They are released in some nuclear decays, and we'll look at that when we get to nuclear physics. And they're also produced in nuclear interactions, and there's a natural source coming from space. So there is a neutrino flux from so-called cosmic sources that hits the Earth, as well as a terrestrial source from radioactive decay. And for a long time, it was theorized that they did not have any mass, these particles. So they were massless particles. But now we know that they actually do have a very teeny mass, much less than the mass of the electron. They are not charged, and there are a couple different types. They're not charged, and they have a very tiny mass, which means they do not interact much with matter at all. Because there's no charge interaction, and because they don't have a lot of mass, there's really no inertial reaction, right, interaction. In other words, collisions, right, are very, very, very scarce. So they're very hard to detect, but physicists want to study these particles. So a typical neutrino detector, you will have this huge volume of material. Often it's water, because water you want an interaction with the nucleus. So water provides a pretty good nucleus for interaction, but also you can get large volumes of it. And you then surround your volume with photomultiplier tubes, PMT detectors. And what you're looking for is you're not looking for neutrinos directly, but you're looking for particles that result when the neutrinos interact with nuclei. And really, you're looking for radiation, photons that result in the interactions. The likelihood of these neutrino interactions is extremely small. So the number of actual neutrino events that these detectors are observing is really low. I mean, really, really, really low. So one of them, and you may have heard about IceCube. IceCube is at the South Pole, and they use large volumes of ice as the interaction medium. And this is from 2010. It's been down there a while. I found this article. But there are over, and this might be more now or less or fewer, I don't know. But at the time, there were over 5,000 PMTs as part of this observatory. Some were looking for cosmic rays directly, I think, on the surface, cosmic neutrinos, but others were actually surrounding this ice volume. And it's interesting, these PMTs were very custom. They were 10-inch, they are 10-inch diameter. I mean, look at the size, that is huge. A generic PMT that you might use in a generic optical experiment might have a detector surface, on the order of an inch or less in diameter. But these things are 10 inches. And you can Google IceCube neutrino detector and read more about it. But there's one of those 10-inch diameter PMTs that's custom made for the IceCube project. So that's pretty cool. I think this is sort of funny. I'll show you. I just did an image source for PMT. I think I put, IceCube neutrinos, something like that. So most of the images are talking about that, but I did get one image pop up with IceCube the wrapper. So I thought that was sort of funny. There he is right there. Among all these pictures of these PMTs and the IceCube experiment. Okay, that's it. I will see you in the next video. Bye-bye.